next speaker is Nick Sheridan. He will talk about the relative Fukaya category, quantum and symplectic cohomology, and
yeah, I can spend the next 15 minutes reading the title. Okay, so thanks for coming, everyone. So I'm going to talk about invariants of Kähler manifolds. So let's remind ourselves what a Kähler manifold is. It comes equipped with two compatible structures. So a complex structure, which is some endomorphism of the tangent bundle, whose square is minus the identity. And this has to be some integrable complex structure, so our transition maps are holomorphic. And also comes equipped with a symplectic structure, which we've heard about in Doris and Mark's talks. So this is closed, non-degenerate two-form omega on our manifold. And we want these to be compatible in the sense that if you plug them into each other like that, then you get a Riemannian metric on your manifold. So on Kähler manifolds, and I can talk about more general things than manifolds, but let's just think about manifolds for this talk. So you can define two kinds of invariants. So some invariants, which are usually called the A model, terminology coming from string theory. So these are invariants of the symplectic structure. They somehow don't depend on the complex structure of the manifolds. We've also got invariants called the B model, which are some invariants of the complex structure. So there's this really strange phenomenon called mirror symmetry coming from physics. It says that sometimes there are these pairs of Kähler manifolds, M and N, and we say that they're mirror spaces if the symplectic invariants of M are somehow equivalent to the complex invariants of N, and vice versa. So these two structures get swapped. Oops. Okay, so let me tell you about, in a little bit more detail, about a specific example of some of these kinds of invariants. They're called closed string invariants. So in this case, the A model, symplectic invariants, are Gromov-Witten invariants of our manifold. So these are invariants which count holomorphic maps of a Riemann surface into M. So some examples which everyone knows, simplest non-trivial Gromov-Witten invariant maybe is the number of degree 1 curves through two generic points in projective space. That's one. Number of conics through 5 generic points in a projective plane is 1. The number of lines on a cubic surface is 27. These are some simple examples of what Gromov-Witten invariants are. And I mean, this talk is about symplectic invariants, but just to say what the closed string B model is, it's periods of holomorphic differential forms on your manifold. So these are some invariants of the complex structure. So I want to just say, one important part of the A model in this case is something called the quantum cohomology ring. So this is some associative deformation of the cohomology ring of our manifold over some ring called the Novikov ring, which you can basically just think about as like a formal power series ring in one variable. And this is the rule, this picture. So the Poincare pairing of gamma with the quantum cut product of alpha and beta is some count of holomorphic spheres passing through cycles A, B, and C, Poincare dual to these cohomology classes alpha, beta, and gamma, and we weight this count by T to the symplectic area of this holomorphic sphere. So that's some element in this coefficient ring here. Okay, so that's quantum cohomology. So now let me tell you about the first time mathematicians kind of got really excited about this mirror symmetry deal. So these string theorists, whose names are up there, considered the case of a quintic hypersurface in CP4, a quintic threefold. So they cooked up some mirror space to this quintic threefold called N, and they looked at one part of the A model, which is really interesting, the number of degree D curves on this quintic threefold. So according to mirror symmetry, this thing that's part of the A model should correspond to something that's part of the B model of this other manifold, and that's just periods of holomorphic differential forms. So that's something you can just write down. So they audaciously made this prediction that mirror symmetry gives the correct answer. The number of lines on a degree 5 hypersurface in CP4 is 2,875. The number of conics is that, and so on. And this was verified mathematically by Giventhal and Lien Yu Yao a bit later in 1996. Up to the fact that there was a mistake in the math literature, or is that what you're going to say?
So the first numbers that you wrote are actually classical.
Oh yes, so I should say that the two numbers I wrote are classical. It's also a computation of the number of degree 3 curves in the literature, which turned out not to be quite the right one.
Degree 3 curves actually was computed after the prediction.
But incorrect.
I thought there was an existing prediction which was incorrect, but it was corrected after mirror symmetry was...
Yeah, but I mean, the paper appears like that.
okay, I didn't know that. Okay. Right, thanks, Alexei. Okay, anyway, independently of these guys already being known by mathematicians, this strange idea coming from physics predicted all the numbers for all D. So this was pretty surprising, and then it turned out to be right. So that was pretty cool. And in fact, Giventhal proved, that mirror symmetry gives the right answers for all Calabi-Yau and Fano hypersurfaces in toric varieties. So, that was great. But in the meantime, in 1994, Kontsevich had proposed his homological mirror symmetry conjecture. So this is a new version. We want to look at different symplectic and complex invariants. So here the symplectic invariants is something called the Fukaya category. So its objects are Lagrangian submanifolds of our manifold. So these are half-dimensional manifolds on which that symplectic form omega vanishes. Morphism spaces are lambda modules or vector spaces. Lambda is that Novikov ring I talked about earlier, and they're generated by intersection points between Lagrangians. And composition maps count holomorphic maps of disks into our manifold with boundary on these Lagrangians. So let me draw a picture just to show you what a composition map in the Fukaya category looks like. So we've got some intersection point P between Lagrangians L0 and L1. So here's some morphism from L0 to L1. And some morphism Q. It's an intersection point between L1 and L2. Then the coefficient of the composition of these two guys, coefficient of some morphism R, is given by a count of holomorphic disks mapping into a manifold with boundary on these Lagrangians, hitting these intersection points at the corners. And again, we weight by T to the symplectic area. So that's our new idea of what the A model is. And again, let me just say, so you know what it is, that the B model in this case should be a category of coherent sheaves on our manifold. Okay, so Kontsevich conjectured that what mirror symmetry should sort of mean is essentially that diagram with the crossing arrows that I drew on maybe the second slide. So we've got our A model here, it's our Fukaya category. It's equivalent to our B model of the mirror manifold N, and vice versa. And it turns out you need to take bounded derived categories to have a hope of there really being an equivalence of categories like this. Okay, he also predicted that this is a good way of understanding that closed string mirror symmetry, those counts of curves that I talked about early on. So he predicted that you can extract this closed string mirror symmetry from homological mirror symmetry by taking Hochschild cohomology. So I'll talk a little bit about this point a bit later. First, let me say a theorem in the direction of that first point, that in this case of the quintic threefold, that was the original motivation for mirror symmetry, there really is an equivalence of categories. So if you take the split closed, so Karubi completed Fukaya category of the quintic threefold, it's equivalent to the bounded derived category of coherent sheaves on the mirror variety, after we make some formal change of variables in the base field. But now, a natural next question after we've proven this theorem is, how do we get those curve counts on the quintic threefold that were sort of so exciting, these kind of concrete numbers coming out of mirror symmetry? And that's not known at the moment. So let me tell you a bit more about what is known or expected about how to get numbers out of these categories. So first I need to tell you what Hochschild cohomology is. So let me tell you what it looks like for an algebra. Given an algebra A, Hochschild cochain complex looks like this. It's a direct product of hom from A to the dth tensor power into A. And the Hochschild differential looks like this. Basically think it's all the ways of plugging the multiplication in the algebra into a generator of this chain complex. So anyway, when you put some signs in appropriately, this becomes a differential, and its cohomology is called Hochschild cohomology. So the first step along the road to getting Gromov-Witten invariants out of the Fukaya category is the existence of an algebra homomorphism from the quantum cohomology, which I introduced at the start, into the Hochschild cohomology of this Fukaya category that we're talking about. So this kind of counts holomorphic disks, boundary on some Lagrangians with intersection points corresponding to some Hochschild cochain, sending P1 tensor P2, blah, 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 around to tensor PD to P0. And we have some internal marked point constrained to lie on some cycle Poincare dual to a generator quantum cohomology here. Okay, so it's not obvious why this is an algebra homomorphism, but it is. Okay. So what I want to think about is a particular type of Fukaya category, one that turns out to be the best way of computing it, the one that allowed us to compute the Fukaya category of that quintic threefold a couple of slides ago. So here you choose a hypersurface called a Donaldson hypersurface. It's Poincare dual to the symplectic form. Define a category called the relative Fukaya category, which instead of counting holomorphic disks with symplectic area, counts them with t to the intersection number of our holomorphic disk with this divisor. And one nice feature of this category is if we set t equals 0, then we get just a complex linear category which depends only on the affine variety m with this divisor removed. So these are the sort of things that Mark McLean talked about in his talk that he studies. So how can we sort of break down this process of getting quantum cohomology out of the Fukaya category using this relative version? Well, if you set t equals 0 in this relative Fukaya category, the Hochschild cohomology is something called the symplectic cohomology, which Mark introduced in his talk. This is something that's independently studied for affine varieties. But when we move to t not equal to 0, we get this Hochschild cohomology, this full thing, which we expect to be the quantum cohomology. This means we really expect there to be some relationship between symplectic and quantum cohomology, which should sort of be the first step in this program I'm talking about. But this isn't understood at all. So I want to start by thinking about this during my time here. So I think that's it. Thank you.